Okay, folks, we are back. So this is the first kinetics experiment that we are doing. And in all likelihood, you've done a lot of problems in lecture, homework, maybe you've already had a quiz on this. This is called the method of initial rates. And not a lot of theory here because you've done this already in lecture in all likelihood. So the main thrust of this pre-lab is really to understand the experimental design and to get a table set up and ready to go so that when you come in and you collect your data, you'll have something that looks very similar to what you've seen in lecture. So then you can handle the calculations on your own, which quite frankly, I'm not gonna talk a ton about because you've done it already and they're laid out pretty well in the lab manual. So let's go ahead and get started. Okay, so kinetics, the speed of a chemical reaction, and the experimental design, which we'll get to, is actually fairly straightforward to perform. It's not necessarily easy to understand why it's set up the way it is. It's actually a pretty ingenious experimental design. So your job is also you're not really designing this experiment, you're trying to understand the design and take the data and do the calculations. But in a very simplistic sense, you're creating a mixture in a 25 milliliter Erlenmeyer flask. I recommend putting something white underneath it to make the color change appear. So you add all the components up. I'm actually not going to go through the mechanics of it because I think you can handle that. You use different glassware to measure the volumes. You put them into the Erlenmeyer flask and you swirl it. And as soon as you swirl it, you hit a stopwatch. And then when it stops, that's how long it takes the reaction to go. The longer the reaction, the slower the rate. If it's a quick reaction, that's a higher rate. So qualitatively, it's a very simple lab. But let's get there. Okay, so briefly, this is just to reiterate some of the theory. The reaction that we're looking at is the iodide ion, and I believe the solution we're going to give you is potassium iodide. So you're not going to see a bottle labeled I minus. You'll see it labeled Ki or NaI. I think it's potassium iodide. So potassium is a sodium, as a spectator ion. Don't let that throw you. We're going to ignore it. So it's iodine reacting with hydrogen peroxide, and I'm pretty sure we give you these two solutions. So the molarity of iodine and the molarity of the H2O2 is known. I'm looking at the procedure now. It's good to have the procedure so you can kind of look along with me. And that's on the second page. Oh yeah, and it tells you to obtain 15 milliliters of stock Ki. Okay. The one thing I want to point out to you there is the molarity in the lab manual is 0.2. You always look at the bottle that you're given on your lab bench. You'll probably have more significant figures than 0.2. So the calculations we're doing here are a rough estimate, but then you can repeat those calculations with the exact molarities that are on those bottles. So please keep that in mind. The manual gives you ballpark figures usually, and then you have to go back and back calculate what you did in the pre-lab. That's pretty common. Remember what stock solution means. That's the higher concentrations from which you make dilutions to lower concentrations. So it's 0.2 molar Ki, 0.1 molar H2O2. Now, those are not the molarities you use in the calculations. Those are the stock molarities. We have to do this calculation to figure out what the concentrations are in trials 1, 2, and 3. I'm getting a little ahead of myself, but just laying out the experimental design. Okay, so the point is this. The chemical reaction is iodine reacting with hydrogen peroxide to produce triiodide I3 minus in water. This is a redox reaction, which we are not going to go and have you balance that. We could. That actually be a good pre-lab question. So if you want to go through and practice redox, you can go ahead and balance this. That's just if you think you need to go back and remind yourselves of that. I'm just going to give you the answer. This is balanced in acidic solution. So we end up putting 2 H pluses here. It's a pretty easy one to balance. And then you end up needing 2 water. So I'm not going through the half reaction method or the oxidation number method that you learned about in Chem 1. But if you'd like to, or if your instructor tells you to go back and balance this. But there's the answer. Okay, so rate laws. Rate laws come in a couple of different flavors or mathematical expressions. This is called we're going to use a method called the method of initial rates based on what's called the differential rate law. Those of you in calculus know what a derivative is, like dy dx, or a change in y over a change in x. In this case, we're doing a change in concentration over a change in time. Okay, that's a differential rate law. Integrated rate law is something else, which we're going to talk about in another lab. So what we do is we have three reactants. So if we write the rate law, we would write the rate law expression as rate equals some rate constant k. This is all in the handout, so you can just kind of listen to this. Some rate constant k, which should be constant through whatever trials you do. That's a double check when you calculate the rate constants. They should be relatively constant. Then you report an average. Times the concentration of, I guess it should go in the same order. Yeah, I'm going in the right order. Just left to right of all the reactants. So it's the concentration of the one reactant raised to a power, and we call that the order of reaction with respect to iodine. The order of reaction is not the coefficient. Sometimes it might happen to be the same value as the coefficient, but that's coincidental. So understand it's not the coefficient. That's an experimentally determined variable, which is your job to figure out. So it's the order of reaction with respect to iodine times the concentration, that's what the brackets always mean, unless it's a complex ion, which I don't know. Raised to that, we're using A's and B's, yeah. And that's the order of reaction with respect to peroxide times the acid concentration raised to its order. Now, the procedure tells you we're doing something a little different here. We're putting in a buffer. A buffer is a solution. We're going to do some calculations with the buffers. The definition of a buffer, I think it's in here, is the solution that does not change its pH. Buffers are very important in nature. They're very important in your body. You don't have buffers, your pH changes in various bodily systems. It causes a medical condition known as death, oftentimes. So what we're going to do is put a buffer in here. What that does effectively is eliminates this variable, because pH is a measure of H plus concentration. We're going to do this later in the semester. So if we hold this constant, we essentially remove that from the chemistry and the math. Okay, it's there to drive the reaction, but we don't want to overcomplicate it. So we're actually going to define a new rate law. We're going to use the same rate, by the way. We'll get to that. But we can't call it the same rate constant, so we call it something K prime. That's what that is. It's not a 1, it's like a, I'm not even sure what that symbol is. It's almost like an apostrophe, but we call it K prime. So it's a pseudo rate constant. So it's not the real rate constant, it's pseudo because we're holding H plus constant. But for all intents and purposes, it's a rate constant. Treat it as such. So, I'm giving this away. The purpose of this experiment is to determine the rate law for the reaction between iodine ion and hydrogen peroxide. That's the purpose. But what does that mean? Well, what that means effectively is to come up with the order of reaction with respect to iodine, the order of reaction with respect to hydrogen peroxide, and an average value for the rate. So you'll find an average value there. That's what it means to find the rate law, is the orders and the rate constant. And then the overall order of the reaction is A plus B. Once you figure out what A is, once you figure out what B is, the overall order of the reaction is A plus B. So if it's 1 and 1, the overall order is 2. If it's 1 and 0, the overall order is 1. Okay. And you follow the data. These are going to be real data. They're not necessarily nice, clean examples like you see in your lab manual. So that's what the goal is. So bouncing back and forth to pre-lab questions, we're in chapter 12. Example 12.5 is one of these problems with 2 reactants, so similar to this. So do that one. It's great. Okay. So there's an example in 12.5 that's worked out for you. And then there's a check your learning, C your L, check your learning problem. Do that. The answer is there. I think even the work pops up. So just redo that. Understand how it works. So if you have 2 reactants, you need a minimum of 3 trials to do the analysis. You could have more than 3, but you need a minimum of 3, and I think we're just doing 3, the minimum, which is all the time we have. I'll let you think about that. Why can't you do it with 2 trials? That doesn't make any sense. You can do 2 trials if you have 1 reactant. Anyway, I'll let you figure that out. Fine. Okay. The experimental design. I should come over here. Just this. I don't want this to be too much of a hang-up. How do we measure this reaction? Potassium iodide is clear and colorless. Hydrogen peroxide is clear and colorless. We do not have a way of detecting this reaction. It won't look, if we just mix these 2 chemicals, 2 reactants together and stare at it, we won't know when the reaction's done. We can't see it. So what we do is we do a side reaction, which I'm calling here an indicator reaction. It's not a great name. Indicators more like acid-base indicators. I guess I could rationalize it that way. But what we're doing is we're doing a side reaction. So here's what happens. You produce triiodide. I don't get too hung up on this. This is the genius of this experimental design. This is designed before instrumental analysis, but this makes the point. It's a great experiment. So triiodide is produced. Well, how do we detect triiodide? Well, we can react it. This is where you don't have to worry about it. The triiodide reacts very nicely with a compound called sodium thiosulfate. Sodium is a spectator ion. The formula is Na2S2O3. We just take the sodiums out, the 2 sodiums out, and we're left with S2O3 2 minus. It reacts with triiodide to produce iodine again, actually, and then, well, an ion that's essentially double the original one. I'm not getting into this too much. The point is this. This reaction will result in a change in color from, so you'll add everything together. I think it stays clear and colorless. You swirl it, and it should change, and you should see it go to a pretty clear, but it might, well, that's pretty obvious, I should say, color change. It might be kind of faint, which is why we put it here. And as soon as you see a blue or black or purple, everybody sees color a little differently. And if you're colorblind, it might just look like a gray color change. So you may need help. If you're colorblind, we have had students like that. I'm not saying that to joke around. It's actually a pretty serious thing if you can't see the colors. Okay. We're actually going to measure the rate of this reaction because you need a number there. Rate is often measured in molarity per second, so moles per liter seconds. Okay, but we have to have, so what we're going to do is we're going to take sodium thiosulfate, we're going to prepare a solution of sodium thiosulfate, we're going to hold that concentration constant through all 3 trials. And when the color appears, that means all of the thiosulfate disappears. Calculating the rate of this reaction is actually really, really easy. Remember, rate is the change in concentration over change in time. And since this is a reactant, the concentration is going to decrease over time, so we always report rate as positive. So we put that there. And change is always final concentration minus initial concentration. Well, in this case, the final concentration, in the lab it says this is set up as a limiting reactant. The final concentration would be what? It's a limiting reactant. 0. So it's going to be 0 concentration. It's all gone. Final minus, well, I guess we can put it like this. S2O3 2 minus initial. In other words, how much concentration is in the flask when you mix it together? That's the initial concentration. We're gonna set that up. Okay, and then the change in time is going to be the final time. I think we're doing this in seconds. I forget what unit we're using. Well, that's on you. I think seconds. Okay, so you may have to change minutes to seconds or whatever stopwatch you use, but that's on you to figure out the units. So this will be a molar, and this will be a negative number, obviously. 0 minus some number is a negative number. That's times that negative, so you get the idea. And then it's going to be whatever time you record with the stopwatch, and the initial time is, well, times 0. So calculating the rate of reaction is actually pretty easy. It's the concentration of thiosulfate divided by time. Okay. So again, genius experiment. Please appreciate the design of this. All right, let's get to some pre-lab stuff. So we're doing 3 reaction mixtures. So table 1 is right there. I'm not going to rewrite that. You've got 3 trials. So look across at the trials, and it tells you what to mix together. And I'm not going to go through the procedure. I forget what instruments you're using to measure each of those things. I think it's something different. Like a graduated cylinder for one of them, a glass pipette for one of them, and an automatic dispensing pipette, with a button and the tip for the other one. Again, I'm not going to do all of that. That's you. Yeah, okay. Now before we get started here, take a look at each trial, 1, 2, and 3 going across. The total volume that you're putting in here should be the same, and you're told to ignore the starch. Okay, there's some experimental error here, isn't there? That these assumptions that we're making about the solution volume. So the total solution volume, which we would call V2 in a dilution calculation, is the same. So figure out what that is. It should be, I think you can ignore the starch. Doesn't it tell you to do that? Okay, I think so, somewhere in there. So again, I'm not doing this math for you, I'm just setting it up for you. So the total volume should be the same for all 3 trials, and it should be some milliliters, and we're going to end up using the dilution equation, because what we want to know, the ones are our stock solutions. So what's the molarity of the stock solution? What's the volume of the stock solution? Trials 1, 2, and 3, it matters which trial. Those you're given those volumes. So molarity of stock, volume of stock, volume 2, you want these molarities because that's what's systematically changed. Oh, and I forgot something. We're giving you 2 of the solutions, and we're asking you to make the 3rd one. We're asking you to make the sodium thiosulfate solution, I think so. Yeah. So the procedure says measure up 0.18 grams of sodium thiosulfate. There's actually sodium thiosulfate pentahydrate, .5H2O. And it tells you to get within a certain amount, like 0.05, I forget. But make sure you measure the correct amount. And you can do the calculation of the molar mass on your own, or you're welcome. So let's assume you did it absolutely perfectly, whatever that means, and you got 0.1800 for sig figs with these balances of sodium thiosulfate pentahydrate, and you prepare this in a 25 milliliter. You should know the sig figs of this by now. And calculate that molarity. That's straightforward solution prep. And you're going to redo that, I think, in calculation number 1 using your actual mass. That's fine. That's fine. So just make sure you know what's going on there. All right. What I'd like to do is question number 5, calculations, is construct a table for calculating the orders as shown in your lecture text. In other words, mimicking one of these examples. It's not going to be exactly like that, but let's kind of go through the mechanics here. So again, I'm not going to put anything in the table about the buffer because the buffer is not doing any reacting. So I'm not going to reconstruct that. So what we want is so like your textbook, the first column, I don't have this pre-written out. So we've got 2 reactants, and those will write them in this order. We've got trial. I'm going to try to fit this in. and they end up taking more space. Trial 1, trial 2, and trial 3. And we've got concentration of H2O2. Well, let's do it in the same order. A concentration of iodine minus, and the units are molarity. let's just think about it a little bit. I don't want to insult your intelligence. But if you look at trials, oh, there we go. So in trials 1 and 2, you're using the same amount of iodine. So your molarities for trial 1 and 2 should be the same. The molarity for trial 3 should be double, shouldn't it? Because you're using twice as much volume. Okay. So fill that out. Your V1 is 2.5, 2.5, and 5. Your M1 is whatever's on the bottom. Now, for these calculations, for this complete table 2, let's just use the molarity of the potassium iodide as 0.2. I'm just reading it out of here. So it's 0.2, right? Yeah. So you know the M1, you have 2 different V1s for 3 trials, 2 of them the same. That's the point, right? You hold something constant and it changes, isn't it? So you can actually fill that out to, I guess, just 1 sig fig. And you may have to change the sig figs on this based on the bottom. That's fine. That's fine. This is just stuff for you to understand what's happening. I'm doing this in a little bit different order. So the next reactant is H2O2. So we're still using units of molarity. What's the situation there? Okay, so I'm just looking at table 1. The volume of H2O2, we're using a little less. We're using half a mil, then 1, then half. So we start out at a certain molarity. Trials 1 and 3 have the same concentration. Trial number 2 has double the concentration. Okay, that's fine. So you're giving your V1s in the table, 0.5, 1.0, 0.5. Your M1 is your stock solution, which is 0.1 molarity. Just looking up at the procedure above the table. I don't know why I'm holding it up. And your V2 is always the same, right? V2 is constant. So you're calculating your M2. So put those there. So again, it should go 1 and 3 are the same, and 2 is double. So you see what we're doing? We're systematically changing these 2 concentrations. And that's what you need to do your differential rate law. The rate, however, now you have a couple of options here. How are we doing the rate of reaction? Well, let's do a slightly more complicated table. So we've got this. I just need more space. So you've got all this stuff. We're completing table 2. Let's not treat this completely like a lecture problem. All right, let's put remember, this is our indicator. The molarity of the thiosulfate, that's not right. The S2O3, oh, it is right, sorry. I thought I was saying it wrong. Sodium thiosulfate, without the sodium thiosulfate, is the same, right? Because we're using half a mil each time. Half a mil, half a mil, half a mil. So those concentrations stayed the same. Okay. How do you know what the concentration is? Well, you calculated. You calculated the stock concentration before. So you know your stock concentration from calculation number 1 or Prelab number 2, whatever it means. So anyway, calculation number 1. The V1 is always the same. You only have to do this calculation once. The V1 is 0.5, the V2 is whatever it is, your M2 is whatever it is. So this should be the same. Because we don't want that to be a variable, we want that to be our indicator of how fast the reaction went. Okay, well, what data are you recording? Well, you're recording time, and I think it's in seconds. So when I say complete table number 2, we're not, you can put data here, here. I'm not going to make up times. You're not going to complete this. So this is going to be, I guess maybe a better word for completing table 2 is set up table 2. And then you're going to calculate your rate. And I might be doing this a little bit too much for you, but I think that's okay with this lab. So when you get the rate, what's the rate? It's this. It's pretty simple. 0 minus the concentration of this, that'll be a negative number, divided by the time minus 0. And actually, I made a mistake over here, didn't I? This should be negative. Negative into negative to positive, so this will give you a positive. So the rate is going to be units of molarity per second. I think we're going to use seconds. So in terms of a data table, this is pretty easy. Concentration divided by time is the rate. Okay. When you do your analysis, when you do the analysis like you did in the book, you're not going to use these two columns. You're going to use the rates of reaction and here and here. So you're not going to, this data is necessary to generate the rates. Usually in a textbook, you're just given the rates and not even told how they were calculated. This is a lab. We're expecting you to go a little bit more. So we get the rates by a limiting reactant that turns the solution blue, and then we go from there. So if you do that, all of that setup before you come to lab, it should be fairly straightforward. I don't think there's really anything in the procedure I want to go through. 25 milliliter Erlenmeyer flask. You've already prepared this solution. Add the buffer. What is it? Yeah, it tells you which instruments to use. So be sure that you know exactly which type of volumetric glassware you're using for the buffer, for the iodide, for the thiosulfate, and the starch is just in a dropper bottle, I think. And the last thing you add is the hydrogen peroxide. Because as soon as you add the hydrogen peroxide, the reaction starts. Now these reactions, some of them can take a while. So you want to get set up pretty quickly, and you can even make some hypotheses, if you will, about which reaction. Actually, this would be a bad hypothesis for like an abstract if you do those, is where would you expect to see the fastest reactions? So when you come in, where would you expect to see the shortest and the longest amounts of time? I think that's it. Everything else is a calculation. You calculate the order with respect to H2O2, I do the total, the overall order, and an average pseudo-order rate constant. And then you do some discussion questions. Yeah, great, okay. That should be good. We'll see you in lab. Just be prepared to quickly get this solution made right away. And I think it doesn't take too long to dissolve, but you want this made immediately, and then get yourself organized. I think you have 3 of these. Label them if you're using this. Trials 1, 2, and 3. Get nice and organized and get going, and then go from there. We'll see how our time is with the lab, but it should be fine to get everything done in an hour and a half or so. But knowing what to do the second you walk in the door is a good idea to get a good start. Okay, that's it. Sorry for my stare, just make sure I wasn't forgetting anything.